In the previous few lectures, we've covered some functional groups and their respective reaction types. For the next couple lectures, we're going to go into instrumentation and analysis, starting first with spectroscopy, which will be the subject of this lecture. There are a couple methods of spectroscopy that you will see on the MCAT. We'll talk about infrared first. Infrared, or commonly called IR spectroscopy, is a measure of molecular vibrations based on the bond types. Below to the right are some characteristic absorptions. Of these absorptions, it's important to take note that alcohols and ketones are going to be the ones that you will likely see. So the 1700 to the 1750 range and the broad 3100 to 3500 range are going to be the ones that you will see. Here's a sample IR spectrum. As you can see, right around the 3100 mark, you see that broadness. This is going to dictate largely based on the alcohol. And over here, you see the sharp peak around 1700, which is characteristic of a carbonyl. Those two in particular are going to be useful when it comes time to look at these charts on test day. As you might guess, if there's an IR, there has to be a UV as well. Although with UV spectroscopy, you will not be asked to interpret the data. You need to know how it works though. It uses UV light and tracks the absorption based on the sample, and it's based on the energy between HOMO and LUMO levels. HOMO being highest occupied molecular orbital, and LUMO being lowest unoccupied molecular orbital. The conjugation shifts the absorption spectrum and it yields higher maximum wavelengths. Nuclear magnetic resonance spectroscopy, or as it's called, NMR. This uses magnetic moments of nuclei and how they align to a magnetic field. An NMR spectrum is going to be a plot of frequency versus the absorption of energy, and it's going to use chemical shift that is measured in parts per million. If it is further left of the graph, it's called downfield, or downfield further, meaning it's de-shielded, with TMS used as the calibration. Note that TMS is used for HNMR, or proton NMR, but there are different types. When it comes to interpreting NMR data, in particular HNMR, you have to measure the area under the curve. This is done by integration, and that area is taken to a subjective level based on the other curves. So for example, if there's one proton, you should have an area that's roughly 1 in respect to the other areas. And if you have 2 protons on the peak, then it should be 2, etc., etc. N+1 rule is used to determine the number of peaks. It's going to determine the splitting pattern. Note that splitting is noted when 2 peaks of identical intensity are not in the same location. A common way to look at the splitting is what's called the 3-away rule. The 3-away rule saying that the splitting is based on the adjacent carbon's protons. Take note that memorizing values and shifts will be helpful, but it's not necessary. What's more important is to know how to interpret splitting and the integration area intensity, and how to correlate these to potential structures. That sounds very abstract, so how about we actually go into one of these examples. As you can see by the highlighted colors, there are 2 protons here. The ones in the middle, denoted by A, the pink ones, are considered to be the same identity-wise, and they are... I'm going to switch ink color so you can see this a little bit better. If you are to see how the splitting pattern would look, we just have to remember the 3-away, or as it is known, N+1. What does the 3-away rule mean? Well, let's think about what kind of splitting we're going to see. Note that both of these protons would be functionally the same for the splitting, and there's 2 of them, which means that there would be an intensity of approximately 2, which is what we observe here, with TMS being the standard there. The 3-away rule simply states that if I were to look at this one in particular, which protons are going to be 3 away? Well, let's check. 1, 2, 3, that's 1. 1, 2, 3, 2. 1, 2, 3, and 1, 2, 3. So that is 4 that are 3 away from this proton, which you would note here. So if this one represents the proton respective, then I would expect to see a split of 4. So 1, 2, 3, 4. Hey, so that's got to be it. How about for B? So B also, just like A, is going to have similar identity. So all of these yellow protons are going to have a similar identity. And there's 4 of them, so we would expect to see an integration value of 4. 3.75, well, that's approximately 4, so that's got to be it. So let's look at the splitting pattern of this one. But note that all the yellow protons are going to have the same expression. Once again, let's do the 3 away. 1, 2, 3, 1, 2, 3. So you're going to see 2 splits, which you can observe here. Based on this, you can likely determine the structure or have a better idea of what the structure is going to look like. On the MCAT, you're going to most likely see a question that's going to ask you to look at one of these data charts and to pick between 4 chemical structures. Being able to understand splitting and what this shielding means is going to likely help you figure out the structure. Note that what it means to be deshielded is that there is density pulled away from it. So if you look at A and B, you'll note that B is more deshielded. What's causing this? Well, as you might guess, it's going to be the chloro group that's attached to that same carbon. Alright, so I know this lecture was short, but it's going to cover the 3 basic types of spectroscopy you're going to see. Honestly, the best way to practice is simply to look at these charts and try to figure out what the structures are. So practice makes perfect for this, just like with all your other subjects. Please join us in the next lecture as we talk about separations and purifications.